Next, number 16. In this one, it's given that x plus iy whole cube equals u plus iv, where of course it's understood that x and y and u and v are real numbers. Then we have to show this: u over x plus v over y equals 4 times x square minus y square. So we start the solution by expanding this cube. If you want, you can write equal to u plus iv, but it's a little cumbersome to keep writing it. Instead, let's just simply expand the cube using our usual formula. So x cube plus 3 times x square times iy plus 3 times x times iy square plus iy cube. So it then becomes, of course, x cube plus 3i x square y plus, what will you get from here? I square y square. I square is minus 1, so that's why you are getting minus 3x y square. And here you have I cube, y cube. I cube is minus I, so that's why you get I y cube. And then you gather the real numbers together and the purely imaginary numbers together. The real numbers are x cube and minus 3x y square, so you write them together. And these two are purely imaginary numbers. From them, if you take I common out, then you are left with 3x square y minus y cube. But it's given that this cube is equal to u plus iv. So equating the real and imaginary parts, you get this: u equals x cube minus 3x y square and v equals 3x square y minus y cube. So now you can understand what we are going to do next. We are going to substitute these expressions for u and v here on the left hand side, and we expect to get the right hand side. So we do just that. We substitute x cube minus 3x square y for u and 3x square y minus y cube for v. And then you notice that you can cancel x from the numerator and denominator of the first term in this sum. And doing so, you get x square minus 3y square. Similarly, from the second term, you can cancel y from the numerator and denominator, and that gives you 3x square minus y square. So x square plus 3x square is 4x square, minus 3y square minus y square is minus 4y square. So that's how you get 4 times x square minus y square. This next one, 17th one, is very interesting. Here two different complex numbers alpha and beta are given. Alpha and beta are not necessarily real. They may be non-real complex numbers, but they are not equal, they are distinct. And the absolute value of beta, that is mod beta, is equal to 1. Then we have to find this: the absolute value of beta minus alpha divided by 1 minus alpha conjugate times beta. So we start the solution with what is given to us, namely this, that mod beta is equal to 1. Then the square of mod beta is also going to be equal to 1, because 1 square is 1. But we know that this quantity is equal to beta times beta bar, beta conjugate. So we are now going to use this fact here somewhere in our calculation, that beta times beta conjugate is equal to 1. So we first take what we want to calculate. That is the absolute value of beta minus alpha divided by 1 minus alpha bar beta. And then you know that mod z1 divided by z2 equals mod z1 divided by mod z2. So that's what we have used in this step. And then in the next step, we have used the fact that mod z, if z is a complex number, then mod z is equal to mod z bar. The absolute value or the modulus of a complex number and its conjugate are the same. So here in the numerator, in place of beta minus alpha, we have taken the conjugate of beta minus alpha. The complex numbers are not necessarily same, but their absolute values are same, and the denominator stays as such. And then you know, by properties of conjugates, this gets distributed over the individual beta and alpha, beta bar minus alpha bar. And now here we are going to bring in beta beta bar, because here there is a 1, alpha bar times 1. So we have written this beta bar without any problem because it's ultimately 1. And then you see in the next step that you can take beta bar common out in the numerator, and that leaves you with 1 minus alpha bar times beta. So you see that the exact same thing you have as your denominator also, 1 minus alpha bar times beta, but there are a few steps. We should not rush for the end. So in the next step, we split this into two parts. The product beta bar times 1 minus alpha bar beta is the product of two complex numbers, beta bar and 1 minus alpha bar times beta, whose absolute value you are seeing here. So that is equal to the product of their absolute values, that is mod beta bar times mod 1 minus alpha bar beta, and this is one of the properties of modulus. Now you can cancel from the numerator and denominator that same thing. That leaves you with mod beta bar, but we know that mod beta bar is equal to mod beta. In fact, that's what we used here in this step. So we have come back to mod beta, which is already given to be 1, and that is why that original complex number, I mean its modulus, is equal to 1. So you have evaluated it. Next, number 18. Here we have to find the number of non-zero integral solutions of this equation. Non-zero integral solutions, that means those non-zero integers x for which this equation will be satisfied. You can already see immediately that x equal to 0 is a solution, because then both sides will be equal to 1. But we want non-zero solutions, and actually their number, how many such solutions there are, that we have to find. So in the solution we of course start with the given equation, and then we first calculate what the absolute value of 1 minus I is. We just apply the formula, the definition of absolute value, square root of real part square plus imaginary part square. Imaginary part is minus 1. So that way we are getting 2 here under the radical sign, or we are getting 2 to the power x over 2, and on that side we already have 2 to the power x. And then after using your usual rules of exponents, actually you divide both sides by 2 to the power x over 2, and then that gets multiplied with this, I mean 2 to the power minus x over 2 gets multiplied with 2 to the power x and gives you 2 to the power x over 2, which is now equal to 1. And this can happen only when x divided by 2, when the exponent is 0. Otherwise it is not possible. So x has to be equal to 0, but we were searching for a non-zero integer x for which this equation is true, which however is not possible, and that is why there is no non-zero integral solution. This is the only integral solution. Next, number 19, which looks very complicated at first, but actually it is one of the easiest miscellaneous exercises. So you see a product of 4 complex numbers, a plus ib, c plus ib, e plus if, and g plus ih. So when you do this gigantic multiplication and gather the real and imaginary parts, you do everything that you need to do. Ultimately, in standard form, that product looks like this, a plus ib. You then have to prove this, a square plus b square times c square plus d square times this is equal to capital A square plus capital B square. It looks like a failed attempt at creating a problem which is worthy of being a miscellaneous problem, I mean which looks very complicated, but actually it's extremely easy. So from that point of view, it's a little foolish also. So what we do in the solution, we start with this, a square plus b square, capital A square plus capital B square, which is not exactly the modulus of a plus ib, but its square of the modulus of a plus ib. So then you write what your a plus ib is, this product, and we are looking at the square of its modulus. Now we know this property of modulus that mod z1 z2 is equal to mod z1 mod z2. In this equation, if you take square on both sides, you get mod z1 z2 square is equal to mod z1 square times mod z2 square. And whatever is true for two complex numbers, that is also obviously true for four complex numbers. You can split this product like this in a few steps. So you do that, and then what is the next step? The square of the modulus of a plus ib is a square plus b square. Similarly, you get the others, and that's it. And finally, the last problem, the 20th one, where we are given this. The mth power of 1 plus I divided by 1 minus I is equal to 1. If this is true, then we have to find the smallest, that is least positive integral value of m for which this is true. That means m is a positive integer for which this equation is true, but maybe for many m this is true. Actually, that is the case. We have to find the least positive m. To avoid unnecessary complexity, let us focus on the number 1 plus I divided by 1 minus I itself. Let's first simplify it, express it in the standard form, and then we will see what we can do from there. So you know what to do. You want to make the denominator real. So you multiply and divide by its conjugate, which is 1 plus I, because the denominator is 1 minus I. So that's how you get this square, and then you expand the square, 1 square plus 2 times 1 times I plus I square. I square is minus 1, which cancels with 1, and the numerator is 2I. And the denominator is 1 minus I square is minus 1, so minus of minus 1 is plus 1. 1 plus 1 is 2. And after cancelling these 2's, you are left with I. So it's a very simple number, it's just I. So that means the given equation reduces to this, I to the power m equal to 1. Alright. Now what are the integers m for which I to the power m is equal to 1? There are actually infinitely many integers for which this happens, and they are precisely all the multiples of 4. We know this fact about powers of I. If you are thinking of where I am getting this from, you go back and see that in one place in the text we discussed powers of I. So from there we find that this happens precisely when m is a multiple of 4. For example, 4 itself, minus 4, 0, 0 is also a multiple of 4, 4 times 0, 12, infinitely many multiples. And among them the smallest positive is 4. That is why the smallest or the least positive integral value of m is m equal to 4. And that completes these miscellaneous exercises. So that means complex numbers, then this chapter is over. So in the next video, we can start something new. So see you in the next video with something new, a new chapter. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.